Hello, this is Mike Walt with LM3. Today I'm going to go over our AI-based inspection system. What I am demonstrating here is the ability of a trained model to detect children's blocks, non-defective children's blocks, in any orientation and any position in the field of view. Notice as I move the parts, they are still detected. If I rotate the parts, they are also still detected. But when I replace the square block with a defective one with a small notch out of it to simulate a molding defect, it is no longer detected. This is the basis of our object detection system. Detect good parts in which the model was trained on, and do not detect bad parts. Further along in the video, I'll demonstrate how we relate the detected objects to what is expected through a calibration process, as well as how the overall inspection process works. In this section of the video, I'm going to demonstrate how the deep learning AI model can be deployed for pass and fail purposes for manufacturing inspection. First step in the process is to collect an image of a golden part. I start this by going to the camera settings. In this case, I have one camera connected, and I go to the camera viewer to view a live image of a set of children's blocks. I start by focusing the camera so that I get a crisp image. That can be done by pressing the settings button, going to the lens tab, and adjusting the focus slider until I get things in as sharp as I expect. I apply the focus setting, press OK, and stop, and save the changes. I can now go back into the camera viewer and get a snapshot of the blocks by pressing the snapshot button. After doing so, I'll be requested where to save the image. In this case, I'm storing it to a local drive, and I'm calling it ABC Calibrate. If I press OK, that image will be saved. I can now exit the viewer by pressing the stop button. And then I can return to the main menu of the configuration by pressing the settings button. Once I'm back at the main configuration screen, I can go into the sequencing options and calibrate the system to be able to detect the objects in an expected location. Start off by adding a new program code. Which I'm going to call ABC. I copy the configuration path from one of the previously calibrated program codes. And I'm going to paste that in to the inspection configuration path for ABC, for the ABC program code. Save. I'm going to go and make sure that this configuration is associated with camera 1, which is the only one I have hooked up in this case, but you can have up to 6 cameras and associate different calibrations with each camera. So I've got everything set straight now, and I'm going to go into TensorFlow settings and go and find the image I took a snapshot of earlier. which is the ABC Calibrate 081419. The location of the label map is usually located on the local drive at Program Files, LM3 Technologies, PAQi, DAQi, Custom Server. I now set the calibration score tolerance, which if I set it to 25 and the system detects objects at 100%, the threshold will be set to 75%. I can set the positional tolerance such that I expect each object in a specific location, with 100 being exact. And I can set the minus score filter to filter out any results lower than 50%. I can also disable the order verification, which is used to verify the objects detected are in a known clockwise order in the field of view. I can set my overlay settings, and by setting the verbose flag, I can see the actual scores relative to the configured scores. So I'm going to leave that checked. And then I'm ready to calibrate the detection model by pressing the Calibrate Detection Model button. After doing so, the model will detect any object that's been trained to detect and report its scores. So in this case, we detected the 4 objects at 100% accuracy, and therefore the tolerance will be set to 75%. Now that I've calibrated the model, I can go ahead and test it by pressing the Test Analysis button at the sequencing screen. The system will then snap a number of pictures in a row and analyze them. I can adjust the display time slider to delay time between snaps. Notice the scores are rather high, 100%, unless an object is missing. 99.97 for the triangle in this case. And when I put the star back in place, there are no more failures shown. I'm running this with the calibration set to detect the order of the objects. So if I go ahead and change the order of the circle and the star, the test fails and displays an out of order message. So I place them back into the original location and all is well. I can also move these parts around, and you'll notice that the overlap score on the second row of the results shows you where the objects are found relative to how they were calibrated. Now, I'm not using the overlap score to determine pass or fail, so I can rotate the full set of parts around, really move them around. As long as they stay in the expected order, the overall inspection will pass. So in this case, it's a little bit hard to see because of the red box, but I've placed the original square block with the defect where the square block is expected, and it fails. If I replace it with the good block, it goes back to a pass state. In this section of the video, I'm going to demonstrate the model, the calibrated model, running in operational mode. So operational mode looks a little bit different. There's a little more space on the screen to display multiple images from multiple cameras. But in this case, I am just using one camera. And I scan a barcode, trigger the system, it takes a picture and performs the inspection and reports the results. In this case, the objects are in the order expected and the inspection passes. I'm going to do that again, enter a barcode, but with the circle and the star reversed. Inspection fails because the objects are out of order, and we are using order to determine pass or fail. Do it again. With the defective square in place, you'll see that the inspection fails. The advantage of this system is it does not require an expert to set up, and the model gets smarter as it is trained more, and therefore it gets more accurate over time. I'm now going to go over some real-world applications. In this first example, we're inspecting molded parts for shorts and defects. You'll notice in this one there is a very small defect towards the bottom left of the object. This one's a very obvious short. And now you get several good parts. Here's another very fine set of defects. And then good parts. More fine defects. You also notice the scores are quite high. In this application, we are going to inspect filters. Plastic molded filters. You'll notice that these first set of parts have flash and some shorts to them. The system's able to detect really small flash instances and shorts that are slightly visible to the human eye, as in this case. This is an obvious one, but the one previous was a small short. Coming up here, you'll see what the end of the filter is expected to look like. This one's close, but it has a little bit of flash on it. And these are good filters. Feel free to rewind and compare the two. Now moving on to welds, both hand welds and robotic welds. This example, we're inspecting welds between a rectangular and round tube. See that these are robotic welds. They pass the inspection. Here's a hand weld that passes the inspection because we trained the model to do so. You also notice that this window looks a little bit different than the others because it is our model evaluation tool, which is used to detect the accuracy of the model. So I let it run. What it's doing is doing its standard detection and comparing it against what's expected. So notice that so far we have 5 expected failures, and they all failed. So we have a 100% match. As we move on here, we are going to get a couple false failures, and I'll zero in on them and explain as we go along. So there's our first false failure. It's a hand weld that looks suspect. And here's our second false failure. Then the number of hand and robotic welds that are okay, scoring at 100%. So when the evaluation is done, I can go and look up the images which represent the false failures. This is false failure 1. This is a questionable weld. So I'm not going to retrain the model or train the model more to allow this because it's suspect. So I'll leave that as a false failure condition, potentially. Here's a second, which also looks suspect. So I'm going to leave that as is as well. This final set of examples includes some parts presence examples. So in this case, we're looking at ultrasonic welds for connecting plastic parts, as well as clips. And this one, we're looking for push pins holding plastic parts together. So you'll notice that the system detects holes as failures and push pins as passes. That concludes this informational video. Please contact LM3 for more information.